Chapter 7, Exponential and Logarithmic Functions. Sections 7.1 and 7.2, Exponential Growth and Exponential Decay. So an exponential function has the form of a times b to the x, where a can't be equal to 0, because if a was equal to 0, we'd have y equals 0, and b has to be a positive number other than 1, because if b was just 1 and we raise 1 to a power, we still get 1. So basically, an exponential function is you need to think of as where the independent variable x is going to appear in the exponent. Every other time we've had numbers as the exponent, but we've never had a variable as the exponent. And so if a is greater than 0 and b is greater than 0, if you think about this for a second, we have a positive number times a positive number raised to a power, so that's going to do nothing but get bigger, and it's going to get big fast. If a is greater than 0 and b is a fraction between 0 and 1, then it's going to get small, and it's going to get small fast. And b is called the growth or decay factor. In other words, b is what is going to determine how fast the function is growing or decaying. So in this first example, y equals 5 to the x, we don't really know what these should look like yet, so let's make a t-chart and graph them and see what they should look like. When we plug in -3 for my x, I would prefer that you did not give me decimals. We should know how to do this. Negative exponent, we learned last chapter or a couple chapters ago that a negative exponent means you put it on the bottom. So we actually have 1 over 5 to the third, which is 1 over 125. When we plug in -2, again, that goes to the denominator, so it's going to be 1 over 5 squared, which is 1/25. 1 over 5. And then remember, when you raise anything to the 0 power, so 5 to the 0 is 1. 5 to the first power is 5. 5 squared is 25, and 5 to the third is 125. So as you look at your t-chart, as x gets bigger, what happens to y? Well, y is getting bigger, so we can see by looking at our t-chart and our numbers that this is going to be a growth model. And so what is the growth factor? Well, again, if you look at the values in the y column, how are they going from one value to the next? We're multiplying by 5, so that's going to be our growth factor. And then we're going to graph these, and yes, I know that it's rather difficult to accurately graph 1 over 125, but it's going to look like that. And if you notice, this line, this curve, is never going to cross the line y equals 0. It's never going to cross the x-axis. And so the line y equals 0 is called a horizontal asymptote. It's a line that the graph approaches but never crosses. In this next example, we are going to have two numbers. So I'd like you to think for a second, can we multiply that 1/3 times the 3 before we raise it to a power? And the answer is, according to the order of operations, no, we can't. Order of operations says we have to take care of that exponent first. So let's go ahead and make a t-chart. And again, you need to realize that you're going to take care of that negative exponent. So it's going to be 1/3 times 1 over 3 to the third. 3 to the third is 27 times another 3 is going to give us 1 over 81. Similarly, with -2, we're going to get 1 over 27. And again, with 3 to the negative first, we're going to get 1/3 times 1/3 is 1/9. Putting in 0 for x, we get 1/3 times 3 to the 0, and still, anything raised to the 0 power is 1, so we're going to get 1/3. And we can keep going along this line of plugging in these numbers for the exponent and filling in the t-chart. And again, as you look at the y column, as my x's get bigger, what happens to my y's? They're getting bigger as well, so this is going to be another growth model. And again, what is that growth factor? Well, when we go from one to the next term, if you look at these bottom three, it's the easiest to see that we're multiplying each time by 3. So my growth factor would be 3. Again, plotting these points, we can see the curve. And once again, this model will never cross the the x-axis, so there's going to be a horizontal asymptote again of y equals 0. Let's do the next example. Again, let's make a t-chart. But now we have a fraction raised to a power. So when you have 1/5 raised to the -3, we're going to flip our fraction. So this is like 5 over 1, or 5 raised to the third power, and we get 125. Similarly with -2, we get 5 squared. 5 to the -1 is going to be 5. Or sorry, 1/5 to the -1 is 5. To the 0. And then to the first power, the second power, and the third power. So again, as we now look at these values, what's happening to our y-coordinates as our x-coordinates are moving to the right? They're getting smaller and smaller. So this is an example of a decay model. And the decay factor, again, if you look at these whole numbers, it's easiest to see what are we doing to get from one term to the next. We're multiplying times 1/5. Again, graphing them, and you can see that it gets small really, really fast. And once again, my horizontal asymptote is going to be the line y equals 0. This next example, I would like you to try. If you're understanding what we've done so far, again, you're going to make your t-chart and plug in those values and go ahead and graph it. And we will talk about this tomorrow in class and compare our answers to each other's. So moving on to exponential growth or decay models when we're dealing with word problems, this is going to be our growth or decay model, where y is going to be the final amount, what we end up with, a is the initial amount, or what you start with, r is going to be percent of increase or decrease, and you need to make sure that you're writing this as a decimal, and t is going to be the time in years. The growth or decay factor is basically in the same place that the b was before, but the growth factor is going to be 1 plus r. It's that whole quantity being raised to the power. And if we're talking about a decay factor, that would be the 1 minus r. Let's review for a minute, changing percentages into decimals. If I have 38%, that's going to be what is a decimal? Yep, 0.38. If I have 5%, remember you're moving the decimal point 2 places to the left, so that's going to be 0.05. 121% is going to be 1.21 as a decimal. And if we had something like 6.8%, that would be 0.068. So in this first example, in 1970, the population of Kern County, California, where Bakersfield is located, was about 330,000. From 1970 to 2000, the county population grew at an average annual rate of about 2.4%. So the first thing I want you to do is write a model giving the population of Kern County T years after 1970. So how do we know which model to use? Well, the key word is that it grew. So if it grew, we're going to be adding inside the parentheses. We're going to be adding the 1 plus our r. When it asks us to write a model of P in terms of T, well, basically that just means that we're not going to use the Y because we're talking about our population. We want to know what our population ended up being. We're starting with 330,000. 1 plus the rate is 2.4%, but written as a decimal is 0.024. And then when we're writing a model, we're just going to use the T because we want to be able to use this model for any given year. Make sure you're simplifying your model, which basically means you're just adding together what's in the parentheses. So this would be our final model. To answer the next question about how many people lived in Kern County in 1990, well, again, you need to realize that T is the years after 1970. So if we subtract them, we get that that's 20 years, and that's going to be what our T is. So using our model, plugging in 20 for T, I would like you to still show me what that full decimal would be. And then we're talking about people, so since you can't have a partial person, we need to be able to round this correctly. And we're talking about 530,290 people. Using the graph to estimate the year when the population was about 400,000, well, that means we're basically plugging in 400,000 for our P. And at this point, we don't know how to solve for T, but this is the whole point in doing this chapter and learning about logarithms is to how to solve for a variable when it's in the exponent. So if you have your graphing calculator, we need to think about how to set the window. If you were to plug into your graphing calculator this model into the y equals, rather this model into the y equals, you're not going to see anything in the standard viewing window. we need to think about how to set that viewing window. So let's think about what the x and y would be. In this case, the x would be our number of years, and our y is going to be our population. Well, our number of years, our x minimum, we can't talk about a negative number of years, so we're going to let our x minimum be 0. And you're going to set this in the window that's right underneath the screen on your graphing calculator. Our maximum, well, after 20 years, we looked in the last example, we had a population of 530,000, and we're just looking for a population of 400,000. So let's set our y max as being 25. That's going to be ample amount of years to get to 400,000. As far as our population for our y minimum, well, we're starting out with a population of 330,000. Let's go a little bit below that and set our y minimum to be 300,000. And then since we want our graph to go at least to 400,000, let's go amply above that and set our y max to be 600,000. Now if you plug this model into the y equals and you go to your graph, you should be able to see the whole graph, and as you scroll over, you're going to watch the coordinates along the bottom of your screen till the y is as close as possible to 400,000, and try to get an answer for that. I'd like you to try this problem on your own, and again, we will talk about this in class, and I'll have you compare your answers to your classmates. One thing that you need to realize, in case you don't know what the word means, if something depreciates, that means it's going to go down. So you're actually going to be using an exponential decay model. So go ahead and try this one, if you will. And moving along to the last example, when you're dealing with compound interest, we're dealing with money in a bank usually, or a loan that you're taking out. So again, A is going to be the amount that you're going to end up with. P is the initial principal amount. R is the interest rate. Again, you need to make sure that you're writing that as a decimal. And N is the number of times the interest is compounded yearly. So when we're talking about the N, you need to ask yourself, how many are there in 1 year? If the problem tells you monthly, how many months are there in a year? Your N would be 12. If it said it was compounded daily, we're talking about how many days are in a year. It would be 365. Weekly? Well, there's 52 weeks in a year. Quarterly? Well, how many quarters are in any whole thing? There's going to be 4. And the last one, semi-annually, I always think about a store that might have a semi-annual sale. How often does Herberger's semi-annual sale occur? It occurs twice a year. So let's look at this example. We deposit $5,500 in an account that pays 3.6% annual interest. Find the account money in the account after 2 years if it's compounded semi-annually. So we want to find out how much money is there. We're depositing $5,500. 1 plus my interest rate, 3.6% as a decimal, 0.036. Semi-annually is 2 times a year. And again, my n is 2 in the exponent, and we're talking about 2 years. Simplifying this if you can, and depending on what your n is, you might not be able to simplify that very easily, what's in the parentheses. And again, you're going to get this decimal. We're talking about money, so please make sure that you're rounding it to the nearest cents, 5,906 cents, $82. If you have any questions, make sure that you are bringing them to class. Don't turn this off yet. I would like you to do the problems that were left undone in the note packet, or if you're not sure how to do them, please make sure that you come with specific questions about what you don't understand. And we will go over those in class. And we'll see you tomorrow.